So CUS plus 2nh3 to give us CuNH3 2 plus Br minus, and I said our K value is simply the product of Kf times KSB, and we calculate that to be this here is 6.3 times 10 to the 10 times 6.3 times 10 to the 9, negative 9, and we said it was 396.9. So now what we can do is we can actually start using our ICE table, right? So we have our K value here, so we can write down our equilibrium reaction here, and we can do our ICE table, right? So I have, because I know it's in equilibrium, I know it's going to dissolve in something. We're given our initial concentration of our ammonia, so this is 0.70 molarity, and we don't actually know our concentration of our copper, right? So we're going to work with this guy here, and we know that our K value is 396.9, right? So again, I'm starting with 0, 0 of our products here. I'm going to subtract x, and then I'm going to add x to these guys here. So I have 0.70 minus x. I have some x here and some x here. And I believe copper should have I'm starting with some type of copper as well, but I'm not given that value here. But I think it's fine for this calculation. And what I can do is I can draw the I can write down our equilibrium expression. So let's check the solution to see what they figured out here. So they wrote the equation here, which is great. They wrote this as well, which is great. So they combined both of them, and they got 4.0 times 10 to the 2, which is about 396, which is good, because that's what we're doing about here. And they wrote down the ICE table, and they have a 2 here. That's actually really good, because the ammonia also had a coefficient of 2, so I forgot actually to put the 2 here, so that's my fault here. Let me erase this. Let's see, how do I erase? Is this a soft eraser? Okay, nice. So I'm gonna erase this, okay. And then I'm gonna do, so this is again a new program for me, so I'm not quite sure how to use this. This is minus 2x here. And this guy should have been, this guy will be minus 2x because of the coefficient here of ammonia. So that's my fault here. Minus 2x here. And then what I can do is I can write the equilibrium expression, right? So I know that K here is going to equal the concentration of our products, which is going to be CuNH3 2 plus Br minus all over our concentration of our ammonia, and then this is going to be squared, because again I have the coefficient as a 2 here, right? So it's going to have to be squared, and these guys are the coefficient is just simply 1, and I know that this guy here was, I believe I wrote down 396.9, so this is 396.9 is going to equal x squared at the top divided by 0.70 minus 2x. Then what we can do is we can isolate this algebraically, right? So I can say, I can move the denominator to the other side. So I would get 0.70, or get 277.83 is going to equal, or sorry, minus, this is 396.9 times 2, times negative 2, minus 793.8 x minus x squared equals 0. And then I can use the quadratic formula to figure out what x here is here, right? So I'm going to do that, and then I'm going to say x here is going to equal, and again, I'm not going to use a small x approximation because I don't know if this is actually quite small enough here. So I'm just going to use the quadratic formula instead. So negative 1, negative 73.8, and 277.83. I'm going to get a value of 0.349 here, and that's the only positive value that I get here. So this is 0.349, 349, or you can say 350. 350, because I'm looking at my significant digits, and I only have 2 here. So I'm actually going to write 0.5. 0.35 is going to be our answer here for molarity. And this is the molarity of our, so this here is the molarity of our of the concentration here. So let me check if they got that as well, and they did. So the 0.34 here, and now we know the concentration of our bromide, right? Of our Br minus here, right? So what we can do is we can actually just substitute. We can do our unit analysis to figure out what our solubility is in grams per liter. So I'm going to take this, which is 0.35, and shift it up here. I'll do this in a different color here. So 0.35, and this is in moles per liter, right? Is in moles per liter, which is the big M here, and I want my solubility in grams per liter. So what I'm going to have to do is I'm going to convert these moles into grams. So in order for me to do that, I'm simply just I'm rearranging I'm solving for my mass, right? For my moles. So you can say that N equals, moles equals mass over molar mass, which means my mass is going to equal my moles times my molar mass here. So I have 0.35 as moles. I'm going to multiply that by the molar mass of, this would be the molar mass of our nh3 here. Or sorry, this is our molar mass of our copper bromide, because that's what we're solving for. My bad. So this is the CuBr that we're solving for. So it's this guy here. So I'm going to take out my periodic table actually and solve for that for you. Because we're solving, again, our end goal was solving for the solubility of our copper bromide. So that's what we're doing here. So it's 63.546 here. So 63.546 plus our bromide atomic mass, which is 79.904. 79.904. And this is in grams per liters here. And then we should be able to solve for this is grams per moles actually. There we go. Because molar mass is measured in grams per mole. So these two guys cancel out. I'm left with grams per liters here, which is going to be, let me use my calculator here. So I'm going to do the 63.546 plus, this is 79.904. And then we're going to multiply that by 0.35 to get our answer, which is 50.20. So this here is our answer, 50.2 grams per liter. This here is our answer for the solubility of CuBr, and this is very close to this answer as well. I might have gotten a rounding error from 0.35 here, and also from 143.45 might not be the exact atomic mass of CuBr, and that's probably the case here. So that's that's the solution for this problem. Might have, again, some rounding errors, so these numbers are slightly far apart, but that's the solution for our first problem here. So this solution is correct, because they're doing the ice table. Well, they wrote down the chemical equation first, and they realized it was a combination of these two. So the K value is simply just the product of these two K values, and then what we did was we simply did an ice table and converted from moles to grams here. So the solution is correct. Good analysis.